All right, hello. So I want to talk to you today about a few key ideas from the labs you've been working on in Pivot, since I'm not here to be a part of your conversations. I want to start with just a couple of terms. So first up, tangential velocity. So where this term comes from is if I draw the disk, and I draw a point on that disk, that tangential velocity is going to be a vector that's at a tangent to the path of that dot. Tangential velocity is going to be measured in centimeters per second. And so it's essentially how fast, in the way that we usually talk about the speed of an object. Now, as you hopefully figured out from the pivot activity, this depends on the radius. So because all of the dots on the disk in Pivot completed a rotation at the same time, the number of seconds it took to get all the way around was the same for all three. But a dot near the edge of the disk had a greater circumference it had to follow than a dot closer to the center. And so a dot near the edge had to be traveling faster. Now, this activity also talked about angular velocity. And this is measured in radians per second, where a radian, really similar to the way you've used it in math, a full circle is 2 pi radians, and then this can be used as a measure of the angle. Now this is independent of radius. So this goes back to that idea that all three dots had to complete a full circle at the same time. So they all traveled a distance of 2 pi radians when we're thinking of angular distance. They all completed that trip in the same amount of time. So they all had the same angular velocity, no matter how far they were from the center of the disk. All right, so now I want to talk a little bit about the graphs. Just make sure you're solid on those. Now, these graphs have a lot of parallels to what we did earlier in the year with linear velocity. So, earlier in the year, we had position versus time graphs. And if I draw something with as a parabola on the position versus time graph, its slope keeps increasing. So it starts out with a small slope, gets bigger and bigger as time goes on. And so that told us it was speeding up because we said the slope equals the velocity. We also assigned some meaning to the intercept of the graph. We said intercept is the position at the time of 0, also known as the starting position. Now from there, we also did velocity versus time graphs, where we said, so like with this one I drew, I start with a slope of 0, and then it gets bigger and bigger, so I have an increasing velocity. Now we figured out the area of this velocity time graph is the distance that the object travels, and we can also add the time. We can annotate this with the change in velocity as well. And we figured out the slope of this is the acceleration. And then, really, really similar to with the position time graphs, the intercept equals the velocity at the time of 0, or the initial velocity. And then we did earlier this year just a little bit with acceleration time graphs, where the acceleration is the slope of the velocity graph. So that should be a horizontal line. I just got a little bit sloppy. Now it turns out we can do some really similar stacks of graphs with angular position. Oh no. So, once again, the slope of my angular position graph is velocity, but this time it's angular velocity. So I'm going to draw that using the Greek letter omega. That's the symbol we're going to end up using to represent angular velocity. And then we're going to use theta to represent angular position, since the angular position is just an angle. And then, just like on linear position time graphs, the intercept is going to equal the initial angle. Now, I can add an angular velocity versus time graph. So I'm labeling it with that Greek letter omega. Now, once again, my graph starts with a slope near 0 and then gradually gets bigger and bigger. So that means my angular velocity starts at 0 and gradually gets bigger and bigger. And my intercept is once again the initial velocity, but now it's the initial angular velocity. My area is the angular distance traveled. The height of my graph is the change in angular velocity. The run on my graph is the time. And then the slope is going to be angular acceleration, which we're going to represent with the Greek letter alpha. And so then I can add an angular velocity, or an angular acceleration versus time graph, which once again is just a horizontal line. A lot of physics teachers like to say that linear motion and angular motion are pretty much the same thing. It's just that angular motion is in a circle and it's in Greek, since we're now using Greek letters to represent our variables. But all of the tools that we figured out with linear acceleration and linear motion are still going to apply. So we're going to end up using these graphs in a very, very similar way. And in fact, on the problems, I went ahead and threw in a couple of linear velocity versus time or linear acceleration problems to make sure we're getting that review on some of that material that'll be on the AP exam. So that's all I have for now. I'm looking forward to seeing all of you on Thursday.